Welcome everybody. We'll be starting in under a minute.
Good morning, good afternoon, good evening, everyone. Welcome to the presentation on fundamentals of earthing design conducted by Elex Software. My name is Edson Fernandez, and I'm the lead technical researcher at Elex Software. Our presenter for today will be Mr. Jason Patrick. Jason is a technical director at Elex Software that develops leading electrical power system design and analytical software. Jason has extensive experience working on large-scale power system projects in high voltage design, testing and commissioning, and power system analysis roles, along with 2 decades of experience in professional software development. Jason holds a master's degree in electrical power engineering, and he leads a multidisciplinary team of developers, cloud architects, UI designers, power engineers, and PhD researchers. Jason's role at Elex Software involves developing new software, complex algorithms for electrical power system design, where he is using a combination of techniques, multiple programming languages, and agile development practices. So in this webinar, we will equip you to have knowledge on all these important points of earthing, such as assessing and mitigating potential safety hazards in system design, optimizing earth grid configurations for different soil conditions, including multi-layer soils, apply best practices in rod placements and grading ring installations, and understands the complex interplay between soil structure and earthing performances. So just before starting the webinar, some general housekeeping rules. If possible, please leave your cameras on so that we have a lively interaction. Microphones will be muted during the webinar. Any questions you have, feel free to write it down in the chat, and we will answer it at the end of the webinar. I will now ask Jason to start the presentation, please.
Thank you, Edson. Thanks very much. I think next webinar we must cut down my biography. I think we've said enough. Thank you everyone for joining. It's wonderful that you could join us on the last technical webinar by Elex Software for 2024. It's been a fantastic year. We've had lots of these webinars. We've had a lot of interest, a lot of questions, a lot of interaction during these events. Please be aware, please type your questions in the chat. We will respond to as many as we can at the end. But we will also note down your name, and if we're able to locate your contact details, which I think we should be able to, I will also personally send you an email to answer your questions. So let's get started on the technical webinar on the fundamentals of earthing design. I'll cover earthing design concepts and calculations with examples. I'll do a case study at the end. It's a very large field, earthing system design. There's a lot involved in it. I mean, there are specialists in this area who spend their entire career working in this field. I think we've come a long way since those days. I think there's a lot better sharing of knowledge in the field and a lot better education. So I think you can become an electrical power engineer, can definitely become proficient in earthing system design and modeling if they undertake some training and maybe a couple of years experience. I think they'll be pretty proficient. So our goal, our aim is to help you with that. Edson already covered the housekeeping rules. Leave your cameras on if you like. We'd appreciate that. Your microphones are muted. Send lots of questions in the chat, please. This event is being one of many. Please register to follow our events at luma/elec, so lu.ma/elec. We will be adding lots of events for 2025 very soon. The outline for this presentation, I will talk about the fundamentals, why we need earthing at a high level. For example, the effects on the human body, what happens during an earth fault. I will then talk about basic or fundamental design concepts, not basic. I'll talk about safety criteria, safe touch and step voltage limits and equations, grid potential rise, touch and step voltages, how to use earth rods properly to improve safety in your design. I'll talk about the safe earthing design process, software modeling and assessment, how that should be done. I'll provide a list, a pretty comprehensive list of standards for power system earthing. This was developed through my own experience over many years and should be a reference, good reference for you. We'll look at example applications of earthing system design and modeling. We'll talk about some slightly advanced topics such as soil electrical resistivity modeling and fault current distribution or fault current analysis. And then, like I said at the end, we will have a case study where I will show you some design and modeling. The software used for the modeling, the plots, the examples is Elec Safegrid Earthing software. It's been around for a long time. It's very, very well-developed, advanced finite element-based software for earthing grounding system analysis. It's accurate and easy to use. It can model earthing systems of any size, above ground, below ground, custom arrangements in multi-layered soils, which is extremely important. It can model low frequency and high frequency fault situations, including lightning conditions. It's fully optimized. It considers the series impedance of the conductors, which is very, very important for accuracy. You can register and download a free trial from our website. Just go to elec.com/electrical software/safegrid earthing, or you can just go to elec.com and go to the software drop-down menu. You'll see Safegrid. The main functions of an earthing system there's three main functions: safety, equipment protection, and system operation. Under the safety category, an earthing system should be designed to ensure any conductors that are accessible, they are maintained at the same voltage or they are equipotential. Also during fault conditions, that any resultant touch or step or transfer voltages that exist during fault conditions don't cause personal harm to personnel or the public. Equipment protection, of course, earthing is very important for switchgear operation and our protection systems. It ensures protective device operation and helps us achieve system reliability levels. It provides a continuous and stable connection to Earth. Conditions of danger for indirect shock. So there are several conditions, and these really fundamentally, these conditions need to occur simultaneously for a shock to occur or potentially occur. So you need to have high fault current at the time, and also high voltage gradient. So if there's a fault entering an earthing system, that would cause high voltage gradients. there needs to be the presence of a person at the time, the duration of the fault, and the contact of the body part or the body of the person needs to be sufficient such that it could cause harm. And there needs to be the absence of any significant contact or series resistance, such as boots or gloves. Those will significantly reduce or limit the any potential dangers for these indirect shock conditions. So really, all of these conditions need to occur simultaneously at once. The probability is quite low. However, still nonetheless, we perform these designs. And also these events do happen. Deaths do occur when these events happen simultaneously. The effects of current on the human body are quite complicated. They have been studied over the past 100 or so years. There are a couple of standards which govern the effects or document the effects. The main standard is IEC 60479. That is not necessarily a power system standard or power systems design standard, but it is used for power systems design and earthing design. They performed studies on human bodies and animals as to the effects of currents. Now, it turns out that the human body is most susceptible to fairly low frequencies within the range of power system frequencies. The human skin is a good insulator with quite a high resistance. However, it only has those properties during dry and when it's intact, and it's easily compromised. The main causes of death during electric shock are asphyxiation and ventricular fibrillation, or stoppage of the heartbeat. Unfortunately for the latter, that condition is irreversible. So it's the more dangerous effect, and it's the one that's considered. So let's look at what happens during an earth fault on an earthing system. So this is a 3D model of an earth grid. You can see the conductors of the grid, how they're organized, and we're simulating a fault condition which is happening in the center. It's actually a switchgear building, and we're simulating a fault that's occurred somewhere in the switchgear building, and earth fault current is being directed into the earthing system. So let's look at these three plots. Longitudinal current. So you can see the faulted conductor. Now, as I said, fault current is being injected there. And what happens is currents are dispersed along the conductors. They travel longitudinally along the conductors, and they're distributed in this network. It becomes an electrical network. The plot in the middle shows the leakage current. So the conductors of the earthing system are in direct contact with the soil. The soil is a conductor, and a portion of the current is leaked or distributed into the soil via the surfaces of the conductors. Now, I should have mentioned that the color of the conductors, red obviously means hot or high magnitude. So you can see the higher leakage currents occur around the edges of the grid. So let's look again at the left-hand plot, longitudinal current. So current is injected at the folded conductor. You can see the red conductors where it's being injected, and it travels along those conductors where red is high magnitude. And when it's being leaked into the soil, you see the higher leakage currents around the perimeter of the earthing system. Let's look at the conductor voltages. Now this makes sense. We've got the faulted conductor in the middle. So we've got higher voltages. And as we move away, conductors that are further away from the faulted conductors or nearer to the faulted conductor, the voltages of those conductors is lower. Now, as a result of the leakage currents, we see ground surface voltages, touch and step voltages. That's what this colored plot at the top. This is ground surface voltage, which has occurred as a result of the leakage of the fault currents via the earthing system into the soil. Let's talk about some fundamental definitions that we need to understand or know about when we're talking about earthing system design. Grid potential rise. Grid potential during the earth fault condition, the voltage of the earthing system increases. That's a simple Ohm's law rule, which is the voltage of the earth grid, which is defined as earth potential rise, a grid potential rise, is simply the fault current times the resistance of the grid. And then as a result of the leakage currents, we get a surface potential. So the voltage of the grid increases, and so too does the soil. So voltage is transferred through the soil, and on the surface of the ground, remember that the earthing system is buried. At the surface of the ground, we have a surface potential, which will be highest nearest to the conductors, nearest to the grid conductors, and will reduce as we move away from the earthing system. So that's surface potential. Remember that surface potential will always be lower than grid potential rise. There is attenuation of voltage between the grid and the ground surface. So there'll always be a voltage drop through the soil and surface voltage will be lower. Touch potential has a relationship with surface potential and GPR. So touch potential is defined as the difference between the grid potential rise and the surface voltage. In the image of the man on the right-hand side, you can see that he's in contact with a steel structure. That steel structure is directly connected to the earthing system. Therefore, that steel structure, the voltage on that steel structure would be the voltage, the grid potential rise, the same as the earth grid voltage. So in other words, his hand is at GPR. His feet, however, are at a different voltage, a lower voltage. They're at surface potential. Now, depending on where he's standing and what surface potential is, nonetheless, there'll be a difference between his hand volt, the potential of his hand and his feet. That gives rise to a touch potential. That touch potential can be hazardous. I'll repeat this a couple of times during this presentation. There are actual touch voltages that will occur during the fault conditions, and there are safe touch voltage limits. And those two values are what we will determine during the design process in order to assess if the design is safe. There's another thing called step potential. Step potential, he's not in contact with the grid, so he's not in contact with GPR. However, he's standing on the ground in some close proximity to the earthing system during the fault condition. So you can see his feet are on the ground, and there may be a voltage difference between his feet caused by the surface potential. If that difference of the surface potential at his 2 feet is significant, then a significant current will flow through his body and could very well cause him harm. We call these, there are safe touch and step voltage limits. We refer to these as safety criteria. There are more or less simple equations for calculating V-touch, which is safe touch voltage limit, and V-step, which is safe voltage limit. Now, these fundamental equations come from IEEE standard 80. I think we have also modified them slightly. And the body resistance and body currents, they come from either IEEE 80 standard or IEC 60479, which is what I mentioned earlier. That was the standard that was based on those studies of someone's drawing on the screen. Please don't do that. Based on those studies of the effects of current on the human body. I'll continue. Oops, now I'm drawing on the screen. So to calculate some of the factors that are in these equations, these are the sub-equations for those. You can find those in IEEE standard 80. I highly recommend that you refer to that standard. It's an excellent reference for earthing system design. There's calculations for foot resistance, and we can include additional series resistances and also surface layer resistivity into those calculations so that we can calculate what is the safe touch and step voltage limits. Now, those will be compared with the actual values, and that will determine if we have safe conditions or not. Let's look a little bit more at grid potential rise. This is a sample, quite simple, pretty small earthing system. Again, as I mentioned, when fault current enters the grid, the voltage of the grid increases. There's a definition here in the third point. The voltage increases with respect to remote Earth. This voltage of the grid is referred to as grid potential rise. And it gives rise, in the bottom right-hand corner, it gives rise to ground surface voltages. As I already mentioned, there's a tip here that Earth surface voltages are always lower. So if we look at this 3D plot, the maximum value here is 2059. That's the maximum ground surface voltage. In this case, we would expect that the GPR, which is the voltage of the grid conductors themselves, would be something higher than 2059 volts. Let's talk about designing to reduce GPR. There are not so many conditions where you need to reduce GPR. It's not such a very significant factor. However, there are conditions where transfer voltages or GPR will exceed the insulation level of cables, etc. in the installation. There is a guideline here that the maximum allowable GPR of an earthing system should be limited to 5,000 volts. As I mentioned before, GPR is a function, it's an Ohm's law function of fault current and grid resistance. So therefore, if we can reduce the fault current or the grid resistance, we can reduce the GPR. This table here just shows some conditions where we've modified the earthing system. So starting from the simplest earthing system, it's the same size, it's a 20 meter by 20 meter, and we look at grid resistance. Now, if we add more conductors, we've simply experimented with adding more conductors. And you can see, I think, row number 3 here, we've gone from a simple arrangement to adding more conductors, but with the same size, 20 by 20 meters. And by adding lots more conductors, we've reduced the GPR by only 14%. I think that's the point of this slide, is that it's really quite a bit of effort or extra cost to reduce GPR by not so much. Another way that it can be done, as I mentioned, aside from reducing earth fault current level, is to increase the area that the grid's covering. Now, this may not be always possible. We may not have the land or the property to expand our earthing system. It also adds additional cost, of course. Land is very expensive. But increasing the area that's covered by your earthing system is very effective at reducing the grid resistance and therefore reducing the GPR. There's another condition here. You can also add rods to reduce GPR or grid resistance, but only if the soil layer, the lower level soil layers are of low resistivity. Otherwise, it's not going to help you much. Let's look at touch voltages and step voltages. Remember, I talked about the definition of touch voltage. It's the difference between GPR and ground surface voltage, where somebody is in contact with the earth grid. They are at some part of their body is at GPR level, and their feet are at ground surface voltage. There's a voltage difference. That's the definition of touch voltage. It's really quite dangerous also because of the pathway through the body, through the heart actually. That's why touch voltages are more dangerous than step voltages. Our tolerance for touch voltage is much lower than it is for step voltage due to the path of the current through the body. The definition of step voltage is the difference in potential between 2 points on the ground surface that are separated by 1 meter. We can see that for this actual design. So these two plots, these two images are plan views of touch voltage on the left and step voltages on the right for an actual fault condition for a simple earthing system. These are the profiles of touch voltage and step voltage. And you can see the magnitudes are quite different. Step voltages are actually quite a bit lower than touch voltages, and that's normal. And also our tolerance for step voltage is much higher. Therefore, step voltages are often, because they're usually much lower and we can tolerate higher step voltages, they're usually not an issue. Especially if touch voltages are not an issue, not a safety concern, or we've mitigated touch voltages, we don't usually have to worry about step voltages, but we can also determine them. Very often during a design, we need to be able to reduce our touch voltages. By one way is to modify the earthing system. So we can reinforce the grid. We can do things like adding more conductors. We can add rods. This is not the only way of reducing touch voltages, but it's one way. And you can see here that the difference on the right-hand side, we've got a simple 4-mesh grid. And below, we haven't extended the area, but we've added more meshes. And we've been able to significantly, well, it could be significant depending on our touch voltage limit. We may have to do this in order so that the actual touch voltages don't exceed our safe limits. And we can do that by reinforcing the grid. We could also do, another tactic or technique is to add a grading ring. So very often we experience high touch voltages around the outside perimeter of an earthing system. That's where our touch voltages are higher. And a reason could be, as we saw earlier, the leakage currents when fault currents are dissipated into the soil, they're often dissipated around the perimeter of the earthing system, and this can cause higher touch voltages around the perimeter. Another reason is that this is the place where surface voltages drop off the most as you move away from the earthing system. So you've got somebody on the outside of the earthing system, so perhaps at the outside the fence. Now the fence is very often connected to the earthing system, so it's at GPR potential. And somebody is standing outside the fence. Very often that could be someone in the public, and they could experience very high touch voltages during a fault condition as caused by the earthing system. So what we do, a technique to mitigate touch voltages around the outside, is to install a grading ring, which is separated on the outside of the earthing system, usually by 1 to 1.5 meters away from the earthing system, outside the fence. And that grading ring reduces touch voltages by smoothing the surface voltage contours. It essentially raises the surface voltages near the feet of somebody standing outside the fence. You can see the difference, the top and the bottom plot, 700 volts versus 400 volts. Just by adding that grading ring around the perimeter, we've been able to significantly almost halve our touch voltages. We can also use rods to improve safety, but I think what this table shows, we've got a simple soil model, two-layer soil model. We're dealing with uniform soil or two-layer soils in this example. And what this plot is showing is that, or what this table is showing is that installing rods are only very effective when you have relatively low resistivity in the lower soil layers. So we are driving rods, earthing rods, from a relatively high resistivity into a low soil electrical resistivity. And then rods are very, very effective at improving grid performance. They can reduce grid resistance, GPR. They can reduce touch voltages significantly if you install rods under the right conditions. You can see on the right-hand side, the very different voltage profiles. This is ground surface voltage when we have different soil layers or different soil conditions. So we've got a low resistivity on a high resistivity. What happens is ground surface voltages tend to stay up in the shallow layers, and they tend to spread out. That's a very different condition to the bottom profile, where you have high resistivity in the top soil layers and low on the bottom. The current wants to get down into the low resistivity soil layers. And you see very different ground surface voltages profiles. But we can take advantage of those, the soil resistivity with rods or counterpoise conductors. Let's talk about rods, rod proximity or the proximity effect. There's also no point in installing lots of rods that are spaced close together. There simply won't be economical. So we don't want to crowd rods. And there's a general rule that you can go by, which we've proved through modeling, is that you don't really want to, or you want to separate rods by at least their length. So if you're installing 5-meter ground rods, you don't want to space them any closer than 5 meters to other ground rods for them to be effective. Otherwise, you're wasting your money and a lot of effort. The safe earthing design process, there is a process that's defined in the standards. it's more or less straightforward and makes sense. The very first step is to collect some basic data, such as earth fault current level, earth fault clearing times, soil characteristics. That means taking soil measurements. This process is defined in multiple standards. There may be some slight variations between those standards. So depending on where you are, you should either refer to IEEE Standard 80 or EN 50522 for Europe or the UK, ASNZS 2067 for your distinct procedures. But fundamentally, as I've mentioned, what we're doing here is we need to compare the actual performance of the earthing system, what happens during an earth fault, what actual touch and step voltages occur, what is the GPR during an earth fault, and we need to compare that actual performance with the calculated safe touch and step voltage limits. And we calculate those limits. You saw the equations earlier. Those are calculated according to the standards. So we're comparing the actual performance against the permissible limits. Now, how do we determine the permissible limit? The actual performance? We often use modeling for that. So we model the earthing system, we add the inputs, we calculate the touch and step voltage limits, the GPR, and we also at the same time, and I'll show you at the end of this presentation, we also at the same time calculate the limits and we do a comparison. And if the actual performance or the actual touch voltages are lower than the permissible limits, we are all good and we have a safe design. So this is an example of the modeling. So we'll model the earthing system. We will calculate the surface voltages. We will calculate the touch voltages. We will look at those in 3D. The earthing system will often be modeled in 3D. I think the system here shows the fence in 3D. You don't necessarily have to model the fence. And we'll look at it in 3D and we'll look at it in 2D, and we will examine areas or locations that are causing problems, such as high touch voltages. You can see in the bottom right-hand corner, the plot, that again, we have the highest touch voltages at the edges and particularly at the corners. We may need to reinforce the earthing system at those locations. So we'll look at those things during the design modeling stage. We will determine GPR, grid resistance. Those are good things to know and to determine. We'll also look at transfer voltages. With the modeling, we can look at transfer voltages. During an earth fault, these earthing systems can often, because of surface voltages, they can transfer hazardous voltages to other locations. Other sensitive locations such as schools, etc. We certainly need to look at transfer voltages. I mentioned schools, but also telecom equipment or metallic pipelines are also other infrastructure where we need to avoid or look into the transfer voltages. If it's a big system, such as a wind farm, transfer voltages could be significant. We need to look at hazardous voltage transfer along fences, to telecommunication assets, to metallic pipelines. We'll need to calculate the overall grid impedance. We can build those models and determine also things like touch and step voltage. I took the time to create 3 slides now for everyone. I listed down what I think, from my experience, are the most important earthing design standards. There are quite a lot of them. And I think if you can, I'd recommend that you take screenshots of the next 3 slides for your own reference. They've been categorized, but I'll slowly move through them. So for substation earthing, IEEE standard 80, highly recommended. Even if you are, you need to follow these other standards. This is a very good reference, IEEE standard 80. For testing, we've got IEEE standard 81. There's some other guidelines that I've mentioned here for touch and step voltage limits. You've also got EG0 for probabilistic calculations of touch and step voltage limits. For renewable energy systems, we've got 3 good standards that I've mentioned here. For metallic pipeline safety, as I mentioned, we need to limit the transfer voltages onto metallic pipelines. So there's a good standard there. And for industrial and commercial earthing, even though we may be working with high voltage systems, we still need to also refer to these low voltage earthing design standards at the interface between HV and LV. For overhead lines, HVDC systems, we've got some earthing design standard there. For data centers, these are very prominent these days. You've got some useful reference standards. For telecommunications, as I said, we need to limit our transfer voltages to those. For fault current distribution, for those sort of calculations, good references are listed here as well. Let's look at some of the applications if we're involved in earthing system design. Some of the applications definitely would be substations. We'd look at GPR, surface touch and step voltages. Transmission lines, these are also modeled. Very often we'll need to determine the impedance of a standalone transmission line earthing system. We may or may not need to calculate GPR, but most often it's a standalone grid resistance, sometimes a touch voltage. Wind turbine generator earthing systems, very often we need to meet a maximum impedance of those standalone earthing systems. So we can model those and calculate them. Very often there's a limit of 10 ohms that's talked about quite often. We may need to design a wind farm. Those are very expansive. We don't necessarily, we certainly can model the detail, include the detail of all the every single wind turbine at the end of these networks, but really it's, as I've shown, it's the area, it's the vast area that's covered by these systems, which really dominates the earthing system performance. As you can see, grid resistance is often very, very low for these systems, even if the soil is quite poor. Solar farms, these installations need very extensive and are of significant cost. These sorts of earthing systems. The earthing system is sort of integrated with the structures, the supports for these for the panels, and those are interconnected with the inverter structures and also the substation to form an overall earthing system. Very often they're quite complicated to model and also to measure. It's actually virtually impossible to measure grid impedance properly. Data centers, that's another application of earthing system design. It's very important to provide proper earthing systems for these sorts of installations. So yeah, we can model the reinforcement, the foundations. If these are properly earthed or combined with the earthing system, then we can consider that as a combined earthing system, and we can determine the performance from there. Perhaps we may want to model a building lightning system protection. We can model a building, the lightning system protection system in 3D, and we can simulate a lightning strike to that system, and we can look at the voltages and currents. An earthing system behaves very differently depending on the voltages. So at 50 hertz power system frequency, you can see ground surface voltages quite uniform. At high frequency, that most likely would be lightning currents. The voltages are actually much higher, but they're actually more contained within a smaller area. The behavior, the profiles, the performance is very much different at different frequencies of currents. So this is how you model a lightning strike, the effects of a lightning strike to an earthing system. It actually happens in the time domain, so it varies with time. You'll see a rise and a fall with the strike. Soil electrical resistivity is a very important, very critical input to these calculations, to the design at all stages. It must be, you must measure soil electrical resistivity very well and reliably. There's some guidelines here as to the probe measurement spacings that you should use. We think it's a very good guide. At your location where you're going to install your earthing system, or as near to as possible, you should measure at least 2 sets of soil electrical resistivity measurements. And because those values, those measurements will directly impact the performance results. From the measurements, what we do is we determine an equivalent multi-layered model. So we input the measurements into software, and we fit a curve, and we say, well, the profile of this soil looks to be 3 or 5 or 2 layers, almost never 1 layer, and rarely 2 layers. It's almost always multi-layered. And this profile affects GPR, grid resistance, touch voltages very significantly. Fault current analysis, this is a little bit of an advanced but very important topic. So I mentioned that the fault current that enters the earth grid directly affects the voltages, or the voltages are directly proportional to the earth fault current. So that earth fault current, very often we are conservative and we assume that the earth fault current level that we should use in our design should be the prospective earth fault current level, which is very high, for example, 15 kA or something conservative or high. But if we look at the system and the earth return paths of the system, depending on the feeders, depending on how the fault current is being supplied, whether that's through overhead lines or cable systems, not all of that prospective earth fault current level will enter our earthing system. Therefore, not all of it will cause touch and step and surface voltages. Therefore, we can vastly reduce our prospective earth fault current level during our design, and it makes achieving safety in your design really that much easier, significantly easier, if we consider fault current distribution. Here's an example system of how it's a cable system. You can simply model this in software. If your earthing system or your substation is being fed by via a cable system, and there's an earth fault at the local substation, that local substation is where we are designing the earthing system. We can do calculations to prove that, say, only 10% of the total fault current will enter your earthing system, and therefore I only need to design a safe earthing system for 10% of my fault current. It's a very powerful approach to simplify compliance and your design. If you are using a software system, I simply added this slide that it must be a good software system. It should be benchmarked. IEEE Standard 80 includes benchmarking. We have benchmarked our software significantly against others, and we have very reliable, accurate results. Now I'm going to show you reasonably quickly what it looks like in software to do a design. So just bear with me for a second. So here you can see our SafeGrid earthing software. So we have a bunch of modules along the top. I'm showing you display results here. But essentially the design process, if you're designing an earthing system using this software, it's from left to right. Essentially, if you're starting, you'll start from the left under design settings and you'll move to the right. You'll move through each of these modules: fault current distribution, soil modeling. You'll enter your soil resistivity measurements. You'll calculate a model. It will automatically calculate the model. It will automatically determine the number of soil layers. You'll build your earthing system. That could be in 2D and 3D. This is a sort of a CAD system. You can also import your earthing system from AutoCAD or any other drafting software. You can modify the system. You can add rods. You can model grids in 3D. The grids don't have to be connected. You can model very complex systems. Here under safety criteria, this is where you'll calculate your safe touch and step voltage limits according to the main standards IEC 60479 or IEEE Standard 80. 90% of the world really should be using IEC 60479. That is the more accurate safety criteria in our view. Another area you will also need to define with respect to your earth grid, where do I want to plot or calculate my surface touch and step voltages? So I use voltage profiles. So I add profiles, and at each one of these points is where I will calculate surface touch and step voltages. Then I'll move to the calculation under display results. So I'll press calculate, and the result of the calculation will be grid impedance. So this earthing system in this soil has a grid impedance of 0.58 ohms. This is the GPR. And what's displayed here is ground surface voltage in 3D. I can also look at it in 2D. And you've got the magnitudes here. I can look at touch voltages in 3D or 2D. So these are touch voltages. I can look at, so there's my safe limit. So I've got actual touch voltages have a maximum of 295, and I've calculated my safe touch voltage limit at 244. I've imported that into display results, and I can check the areas where of my grid that are exceeding the safe touch voltage limit. Now I need to mitigate those. I need to modify my earthing design such that no touch voltages exceed that safe limit. I can look at step voltages. Yeah, these are not an issue. There's nothing except you can see the safe limit for step voltages is really, really high, and my step voltage limit is really quite relatively low. Step voltages are rarely an issue, but we can calculate them. We can plot them just for our clients' benefit, usually. Grid plots. Let's look at grid plots. Remember, I talked about what happens during an earth fault. So I can look at leakage currents. It looks like the currents, the fault current, a lot of the fault current is leaking out through the rods. So the rods are really, really effective in this design, in this case, under these soil conditions. We can look at longitudinal currents. So it looks like, so we've got more red down this area. It looks like the fault current or the fault occurred somewhere here down in this area of the grid. We can, of course, move it anywhere we like. We should locate the fault at the where it's most likely to occur, for example, at the switchgear or at the transformer, for example, with respect to the earthing system. Remember, our switchgear and our infrastructure is installed on top of this earthing system generally. We can look at segment voltages. Again, my voltages are highest near where I've injected the fault. There are a bunch of other reporting tools that are part of this software as well. But essentially, as I mentioned, you start from left to right, enter your data, end up with display results, calculate the performance, compare the performance with the safe limits, and if you have an issue, move back to the other modules, make a modification, come back and recalculate, and hopefully you have a safe design. That's the earthing design process. So I'll finish it there. I'll start answering your questions. I think there's been quite a lot. Edson will ask me the questions and I'll try to answer them.
Yeah.
There looks like a lot.
Yeah, we'll answer a couple of questions, and the others we will send them a reply.
Yeah, sure.
Okay.
I mean, copper has very good resistance to corrosion. I would be recommending copper. It's good for almost anywhere.
Okay, another question is, does our modeling take into account the internal impedance of the conductors?
Does our modeling consider the internal impedance of the conductors? Yes, it does, and that's a very important factor. You need to consider the voltage drops along your earthing system conductors. Very few software packages do this. They assume that the voltage at any point in the grid is the same. Now, when you start dealing with large grids, or you have grids that are installed in low resistivity soil, the voltage drop along the grid is very significant and you need to consider it.
Yeah, the next question is like, if you control step.
Okay, so in other words, if touch voltages are safe, can we assume that step voltages are safe always? Not always, but most often.
The other question is, if you have a wind farm grid, why do we have to connect it to the main substation grid?
Well, okay, so why would we have to connect a wind farm, earthing system to a substation grid, right? Well, they for the benefits, right? So we want to have our earthing system or earth grid impedance as low as possible, and wind farm earthing systems cover a vast area, and they can reduce our GPR touch and step voltage limits significantly. However, generally when we're doing the design of a substation for a wind farm, we need to do the design in isolation of the wind farm first. So we can't 100% rely on the fact that the substation will be connected to the wind farm. But at the end of the day, it will be interconnected. So what we model, what we design will be conservative because it will be in isolation. And then afterwards, we will connect everything together and everything should perform even better.
Yeah, we'll take one more question is regarding the split factors
Yeah,
of fault currents in cables.
yeah.
How are we doing that? And the related question is, do we do the fault current distribution based on the current fault level, or do we have a prospective rise in fault current, for example, 20 years down the line? Should we design with that scenario?
Okay, so there's a few questions in that. So fault current distribution for cable systems, how do we do it? Well, we model the cable, but in a simple way, we model the conductor and the screen, or the earth return. So usually it's the screen of the cable or the armor of the cable or the sheath of the cable. So we need to model the conductor and the sheath or the screen of the armor only in its dimensions, so its diameter and its series resistance. And when we know the separation between the screen and the main conductor, then we can calculate the coupling between those two conductors. So what happens when there's a fault on the face conductor is there's a mutual impedance or a coupling with the screen, and a high portion of the fault current is returned on the screen to the source and doesn't enter the earthing system where the earth fault is. So we model the cable, we model the sections, we model the earthing system at the ends and any intermediate earthing systems. We can also model overhead transmission lines. We model all that. It's essentially like a circuit analysis. It becomes like a nodal circuit analysis. We calculate all the voltages and currents. But one value we're really interested in is the voltage that enters the grid. What was the other questions as part of that?
The prospective fault current over 20 years.
Should we consider the prospective fault current now or in the future? I think in our software, you can enter a future increase or allowance. I think some of the standards, for example, the UK standard 50522 requires you to consider the future allowance. I think it's a good idea. It's not mandated everywhere, but look at your specifications and talk to your clients about it. Be they utilities, they may have a requirement of 10% future increase, for example. We will wrap it up there. We have a lot of questions. We will, as I mentioned, if I can identify you through the chat, I will personally email you. Thank you so much for your questions. Thank you very much, Edston, for going through all the questions and for being with me on these events for 2024. Thank you everyone for your attendance. We really appreciate it. We will see you in 2025. We have lots of events coming up in 2025, lots of free technical events where we're going to be providing more and more value to you. Thank you. Merry Christmas, Happy New Year, and we'll see you next year. Thanks, everyone.
Thank you, everyone.